So it leaves us with a bit of a quandary, which is all of these methods have issues, from the visual inspection to the 4 millimole to the IAT and so on. And as I say, there are an array of methods that one could adopt beyond those, but all of them really do have inherent issues because they're very much dependent upon the protocol that you use, the method of analysis that you use. So these all play into issues related to validity and reliability. And as I say, these are all approaches and methods to identify the same point. And you can see the difference here between using something like an obler at 4 millimole to, for example, doing what's called a Dmax test here. Huge difference, but they're meant to be identifying the same point. All of these are fundamentally going to be dictated by the increments that one uses and where the sampling takes place. But this is really problematic, and all of these fundamentally have their own limitations in the test-retest. Some of these are mathematical derivatives, some are perhaps a little less mathematically orientated and are related to kind of fixed concentrations and so on. And when we take that same data, you can see the inherent variability within this. This is kind of underlying the ability of these tests to kind of be replicated, and the inherent variability that we see in all of these. So here you can see kind of the inherent variability across these range of tests, and you know they are large. You know, the effect sizes that you're looking at here. Okay, one could argue, you know, they're not all particularly large, but you know, we've got large effect sizes in here at obler at 4 millimole. We've got a large effect size here as well. Some of these are in the moderate to small effect sizes, but you know, if we get anything which is kind of a large effect size, it's telling us there is inherent variability in the data that we're trying to look at. And we mentioned right at the start about the way in which the concentration is recorded, and this is actually a nice data set. It's a relatively recent data set, and they've compared a range of devices to record the blood lactate response. And so this is quite an interesting, you know, outcome, and they've identified for us what they call lactate threshold 1 and lactate threshold 2, so LT1 and LT2. But you can see there are inherent differences. Down at the lower intensities, there's pretty good agreement. But as we get to higher exercise intensities, look at the differences here in these devices. Now, one could argue, well, that's not a problem if I'm trying to identify these lower workloads. Agreed, but there is still a little bit of variability here. Excuse me, but it does seem to suggest in the kind of the more steady state orientated exercise that we are probably okay using these range of methods, but as I mentioned right at the start, for internal reliability, stick with the same one. But if you're looking for maximal concentrations, there is an awful range of responses that you can see here. And then what about if we compare a lab-based analyzer, which is a good kind of industry standard analyzer, which is something like the Biosin series. We use Biosin in our labs, against perhaps a more clinically orientated device, which is something like the YSI. And so there should be good agreement. And what they've done here is they've just looked at these across a range of concentrations, not during exercise. So what we can see is there is really good agreement. There's a really good correlation between these two. Now, correlations have their own inherent issues, but actually it does really kind of suggest to us that these two devices in particular have very, very good agreement. They're both benchtop analyzers, and so one would hope that they do have this kind of agreement.